Welcome to another video of mathematical problem solving. In this, we'll be looking at the geometric area problem. What does that mean? Let's get a look. So this is a problem from one of the AMC papers, and hence the use of the letters AMC for the triangle, if you were wondering. So let's read the question. Triangle AMC is isosceles, which means two sides are equal, and those two sides are AM and AC. Medians MV and CU are perpendicular to each other. So median is a line that connects one vertex with the other side, the opposite side. So in this case, if you take MV, M is the vertex which connects with the side AC, but it connects at a very specific point. It connects at the midpoint of the side. So U and V are midpoints of AM and AC respectively. There's something unique about this problem. The medians are perpendicular to each other. MV equal to MC equal to 12. So not only do we know that the medians are perpendicular, we also know their length, it's 12. Now the question says, what is the area of AMC? That is what we need to find out. What's the area of AMC? You can pause here, try to solve it. And if you did solve it, you can leave a comment with your solution or how much time it took you. But my goal here is not just to solve this problem, but also to show you the quickest and the easiest and the most sturdiest, stablest way to solve this particular problem. But in order to solve this, it's not like your typical problem because there's a lot of geometry involved. You've got to think about isosceles triangles, medians as perpendicular, medians that kind of intersect at P. All of this have to be taken care of. And to really solve this problem fast, you need to understand something much deeper. And hence, this is a geometric problem solving. It is not just a simple area problem. It's not so much mensuration, which means measurement, which is where typically you'd see the area problems, but it's more of geometry. So first, let's try and do that. So the first part of the problem is when you prove this. Prove that the area of any quadrilateral whose diagonals are perpendicular to each other is half the product of the diagonal. What does it mean? A quadrilateral has two diagonals. Those diagonals are perpendicular to each other. And if they're perpendicular to each other, then the product of the lengths of those diagonals divided by 2 is the area of the quadrilateral. This is a geometric proof. How do we prove this? Let's go ahead. When you think about perpendicular diagonals, usually I think of rhombuses like this, right? But we can't take a proof for a rhombus. We actually have to assume that it's an irregular quadrilateral, something like this, and prove it for this. If you prove it for this particular quadrilateral, then it's going to be true for every rhombus and square, which also has perpendicular diagonals. So let's call this A, B, C, D, and intersecting at point I. Okay, let's take the first diagonal, the horizontal diagonal, which is AC, and let's give it the length D1. Let's also divide this entire thing into two triangles, right? The moment I think of the AC diagonal, it's dividing the entire quadrilateral into two triangles. Let's call the length above as x and the one below as D2 minus x, because D2 is the length of the other diagonal BD. Now, since they are perpendicular, x is perpendicular to AC and D2 minus x is also perpendicular to AC. And therefore, it applies that, the law of finding the area of a triangle, which is half time base times height, should be applicable to ADC. So ADC is nothing but half times D1 times x. And ABC is nothing but half times D1 times D2 minus x. I hope this is very straightforward. Now let's think about the entire quadrilateral ABCD, which is nothing but the sum of the two triangles. So if you look at the common part, which is half times D1, taking that out of the bracket, what you're left with, the uncommon terms, which is x plus D2 minus x. X cancels out, and therefore you have the area of the quadrilateral to be half times D1 times, hence proved. Now, similarly, let's think about the area of a quadrilateral. Now, how do we apply this? We learned that particular. How do we apply this? So we construct a line. We connect U and V together. We know that MUVC right now is a quadrilateral. And guess what? It has perpendicular diagonals. And perpendicular diagonals, we just proved that if you could just multiply both the diagonals together divided by 2, that would be the area. So the area of quad MUVC is 72, and we did that in a jiffy thanks to our understanding of geometrical principles, which we just proved in the previous slide. Okay, so now that we know that, what else do I need to prove to find my solution? So I need to prove that the ratio of the areas of similar triangles is the square of the ratio of the sides. Let's do that. So let me take two triangles which are very similar, one brownish and one greenish. So these two triangles have a ratio of k, which means if you can think of any one of them, if you take the larger triangle and say the base is capital B, then the smaller one could be capital B divided by k, or the smaller one is smaller b, then the larger one is kb. The ratio of the heights would also be similar because similar triangles have similar ratios for every linear side, whether it's the height, whether it's the side. Now the area of ABC, let's take the larger triangle, is half times the base, which is capital B, the height, which is capital H. But we just learned that the capital B is nothing but b times k, where the small b is the base of the smaller triangle, and h times k, which is the height of the smaller triangle. And therefore, I have half times base times height times k squared. And what is half times base times height? That is nothing but the area of the smaller triangle. So the area of the smaller triangle times k squared is going to be the area of the larger triangle. How do we apply that here? Let's think about it. The area of AUV, which is the smaller triangle, is similar to the larger triangle, which is AMC. And AU is to AM. AU is to AM, because remember, U is the median there, is nothing but half. So the ratio of the area has to be 1/4. So the area of AUV, the smaller triangle, is going to be 1/4 the area of the larger triangle. Let's bring all of this together to find out the area of triangle AMC. AMC is nothing but AUV plus MUVC, as in the smaller triangle plus the quadrilateral beneath it. We know that the quadrilateral is 72, we proved it earlier. We know that the area of the smaller triangle is 1/4 of the area, and therefore solving the simple algebraic equation will tell you that the area is 96. Lessons to learn. Building blocks are needed to solve mathematical problems. We are all about fluid intelligence being the ability to build stuff from scratch, from ab initio, but you don't have to do it all the times. Sometimes crystallized intelligence can be used. Crystallized intelligence are already built bricks and blocks, right? So you already have it. And when you do a lot of math problems, not only would you develop your fluid intelligence, you'd also develop your crystallized intelligence, especially in topics like geometry, where there's a ton of proofs, trigonometry when there are a ton of identities. You can't keep deriving each one of them. Learning how to use these building blocks together is also problem solving. So your mathematical journey should not only be to develop your skills of how to build and solve problems, it should also be to build a vocabulary and a library of insightful proofs, insightful identities, and things that we accept as the basic truth, which definitely will help you solve problems much faster. I hope you found this video useful. I look forward to seeing you in the next one, so please do subscribe and click on the bell icon so that you don't miss out. Do share it if you found it insightful. Thank you.